Go ahead and label the quadrillion angles like I have, the decimal forms. That's pi over 2, that's pi, 3 pi over 2, 2 pi. You don't do it every time, but this particular problem, you want it. It'll be helpful. And we're going to make a table. And in the table, I'm just going to put the angles, quadrillion angles, but in exact form. But when we do the math, we will use the decimals that I had you write down. Well, when r is 0, you get 2. 0 plus 2 is 2, so plot that point. When you plug in pi over 2, well, that's really 1.57 plus 2 is 3.57. So I'm saying when you rotate it so you're facing due north, you'll go out that far. Oh, I forgot. I keep forgetting. We need to rescale our axes for this one. So actually make it scale like that. So 2 is actually going to be here. Hopefully you're using pencil. And 3.57, look, this is 2, so that's 3.57 is about there, okay? Questions? Look. The equation says r is just 2 more than theta. And you got to remember, theta is these radian values. So when I was at 0, I just did 0 plus 2 to get that 2. When I'm here, pi over 2 is actually that number, plus 2 is that. When I get to pi, pi is 3.14, plus 2 is 5.14. So when I've rotated in that direction, in the direction of pi, I'll go out 5.12, which, once again, that's 2, 4, this is 5 in the middle, so a little bit beyond that. What's the next value? Because, exactly. So 2, 4, 6, and go not quite halfway, because that'd be 7. And then 8.28. Which is a little bit beyond 8. On the spirals, that's what I expect of you, is do basically from 0 to 2 pi, all the quadrillion angles. And this one spirals out, you can see. Yeah, you must connect them. Listen to me. When I said I expect these points to be plotted, it's true. That's my expectation. The table's optional. I'm just saying, if the directions on the problem just say to graph this, make a table if you want to. You don't have to. You can do it all in your head. That's great. But those 5 points need to be there. All right. Now, if the directions say you have to fill in the table, then you have to fill in the table. I'm saying otherwise you don't have to. All right. Number 4, we're going to replace as well, because number 4 is just a circle, right? We've done that. So replace it with this. Now I'm going to make another table. Same angles. Now, frankly, with 0, I'm not going to fill anything in because it becomes 4 minus 0, which is 4. That's just easy. This one, I'm going to show the work. I'm going to plug in my angle here. And here I'm keeping it in exact form instead of decimals, obviously. What is this? Right? 1. So you get 4 minus 1 is 3. So when your angle is pi over 2, so you're facing due north, you go out 3. Let's move on to pi. Take the rule, plug pi into it. I'll make it look like a fraction. Cancels, you get 2, and then 4 minus 2 is 2. So when you're facing the direction of pi, you go out 2. So you can see now, hopefully, that it's spiraling in. I'm going to go and show the math all the way down. You should be able to do this arithmetic. Pi's cancel, 2's cancel, you get a 3, 4 minus 3 is 1. And the last one, you plug in 2 pi, the pi's cancel, you get 4 there. 4 minus 4 is 0. So, like I said, you can see it's just spiraling in. Something like that. I'm not sure how tight to make that. Okay, I'm going to stop. I keep messing it up. Okay, so there's your spirals. Well, yeah, it's not going to be straight. right? And actually, let's talk about that a different way for a second. If you did that, like that, that's not possible because r is a function of theta, and you'd have, well, see, it's not a function, then you can't have that. Okay, maybe I shouldn't talk that way because it's kind of overlapping in another sense. No, not really. The graph overlaps, but for r equal that particular number, we do get one answer, even though the graph overlaps. Yeah. Yeah. But look at this. We're not going to draw something like this, but this is still a spiral. What I want you to appreciate is that basically, if your function is one that's just an increasing function, in your exponential functions, when you drew them normally, it look like this. They just increase forever. Well, then when you put it on the polar plane, it'll just spiral out. Okay, so you know, if I did theta to the power of 3, that just increases forever. It'll spiral out. So you can get all kinds of spirals, really. By the way, just for the record, E is that number 2.718 something. It's like pi. It is a special pi, if not more so. It's up there in that kind of ranking. It's a very special number in mathematics. Euler's number is called. All right, lines. You already, well, you did this kind of line. That we just replaced it. Number 1 looked like that. We replaced it. That would have been the graph, though, right? Number 2 actually is another line. This one. Oh, that's right. Hold on. One thing I want you to do. Or here, watch. One thing you're supposed to know. Very basic thing. You're supposed to know cosine of theta is x over r. You're supposed to know sine of theta is y over r, right? But that means x is the same as r cosine theta. Write that down. Y is the same as r sine theta. So knowing this is just equivalent to knowing this. The same knowledge, just written a different way, yes? But that means this is really just y equals 2. Which means it's just a horizontal line going through 2. You don't have a grid, but hit 2 on the y-axis. It's not really the y-axis, but it'll do. Technically, this is the line that equals pi over 2. Doesn't have a name, it just has an equation, but there you go. Now, the other thing I want you to be able to do is take this equation and write it as r equals. Well, you just divide by sine, you get 2 over sine. But we wouldn't write it like that. We'd write it as 2 times what? Secant or cosecant? Say it again? Cosecant. Instead of cosine is cosecant. So write it like that. You should be able to write it as r equals. But you'll see it both ways. And once again, this way, you just look at it and realize that's just y. Next one then, that's really just x equals negative 3, because r cosine theta is x. So you just have a vertical line going through negative 3. But if you write as r equals, you get negative 3 times what? Yeah. So like I said, your polar equation will come in both forms. This form is not nice in a sense, except for you can see it's x equals very easily. This one is harder to see, you know, that it equals a vertical line, but it'd be easy to have in the calculator. Circles. Number 4, we replaced because we've done that, right? R equals 3, just the circle center at the origin. This would be a circle as well. Listen, we're going to actually plug in some points, like actually calculate some points, but not many. When you get to the cardioids and limit we'll actually plot and calculate more points. First of all, I plug in 0. What is sine of 0? 0. So you get 0. So we're at the pole initially. I want to skip over pi over 2 for now. No, actually no. Skip over pi over 4, I meant. And we're going to do pi over 2. What is sine of pi over 2? 1. And so the radius is 4 there. 4 times 1 is 4. Which that's the biggest distance from the pole. And then 3 pi over 4 we'll skip over as well. Pi, what's sine of pi? 0 again. Actually, this thing's going to be a circle. We just finished the whole circle already. What I need to do is put the center here. And you need to go out. The radius is 2, obviously. Here's horizontal distance 2. You kind of need to line up with that. So hit this line. Line up with this. Be like right about there. And come over here. and try and line up with your center, and line up with this, and it's like right about there. Because it's a circle, and I want a well-drawn circle, so I need inputs of that diameter. And our table really didn't tell us it's a circle, didn't give us much, but I'm telling you, you should know it's a circle. And I'll help you fill in some more of the blanks. Before I do that, look at this. If the equation has sign in it, you should know it's symmetric about this line, theta equals pi over 2. And if it's a positive coefficient, it's above, like that, it's going up. If it had been a negative 4, the circle would be down here. If it had been cosine, it would be either here, it's positive, or here, it's negative, okay? So that's really what you just need to know. By the way, what is the 4? It's the diameter, isn't it? Right, the radius is 2, not 4. Unlike here, where the number you're looking at is the radius, here you're looking at the diameter. Now, I want to go and fill in these blanks. The catch is, if I do sine to pi over 4, it's square root of 2 over 2, right? So here, so we do 4 times square root of 2 over 2, ends up being 2 radical 2. What I want you to write down somewhere, like in the top of the paper, is just that square root of 4 is around 1.4, and square root of 3 is around 1.7. Those are really rough estimates, but that'll be good enough for this. If that's true, then 1.4 doubled is 2.8, isn't it? So when I plot that point, you go out along that line, 1, 2.8. That's another way to know where that point belongs. And over here, it's the same thing. It would be symmetric, so you get 2 radical 2, which is 2.8, which is why that point's where it is. So then you have something more to go on just beyond your memory. One more thing. If I'd kept going, what I would get is like, here, I'll just do 3 pi over 2. Sine is negative 1 there, right? So when I'm facing due south, my radius is negative 4, which means it hits this point again. That's what it really does. As your angle rotates through that, you hit these points on the circle. As your theta goes from pi to 2 pi, your radius is negative all through here. Why is it negative? Because isn't sine negative? And so you end up tracing with the circle again. So you don't need any more in your table. All right, next one. It's cosine, so it's centered on the polar axis, and it goes left. And the diameter is 2, so put a point here at 2. Here. There's the center. Radius is 1. Line it up there. Like I said, I'm trying to line up with this because the radius is supposed to be 1. Here's the center of my circle, and I'm done. That's what I'm saying. That's all the time it should take you. If it looks like this, you should know it's a circle. Cosine is horizontal, so to speak. Negative means it goes left. And then one above, left and right from the center. Yeah. Exactly. And obviously, we could have done the first one the same way. Just realize it's up because it's sine and with positive, and the diameter is 4. So the center is 2 above, and you go out 2 left, right, above, and below from that center, and boom, you're done. So plotting, calculating the points if necessary. All right, this kind of equation. If they're equal, you have cardioid. If the first thing's smaller, you get a limit on with a loop. If the first thing's bigger, you get a limit on without a loop, but there's actually 2 different kinds. Kinds that have a dimple and kinds that don't. Okay? But either way, if A is bigger, you definitely don't have a loop. And I showed you that. If you take a circle, like you could, and trace it like 1 quarter, rotating around another quarter, that point would form a cardioid. So, all right, what is this one? Yeah. And I gave you that sheet, that note sheet that spells all this out. When you're doing the homework, before you do anything, you should try to identify the shape. Because in here on these, the cardioids and limicons, we're going to make a table, and we're going to plot points. But once you get the points, you need to know how what shape they're supposed to form, because otherwise it can be very confusing. Okay, so right here. Now, as far as making this table, you can see I didn't choose everything. Why did I choose pi over 3 instead of pi over 6? It's cosine. What's cosine of pi over 3? A half. So I'm saying I want your quadrant angles in your table, and then you have three angles in there that you know, pi over 6, pi over 4, pi over 3. I don't want to use pi over 4 because it's square root of 2 over 2. And I want to do square root of 3 over 2 over either, right? So I'm saying on the cosine graph, choose to use those angles because they're nice. So let's do this. What's cosine of 0? 1. So we actually start out with 0. Okay? Then we said we plug in pi over 3, cosine would be 1/2. And that's a 1 then. 2 minus 1 is 1. So if we rotate towards pi over 3, go out 1. Okay? Now plug in pi over 2. What is cosine of pi over 2? Cosine of pi over 2. On the unit circle, cosine 0. Cosine of pi over 2 is 0. And so you get 2. And the distance of being 0, 2 minus 0 is 2. So when you do north, you go out 2. Now, we're doing cosine. Cosine is positive on the right, negative on the left. So I'm saying if it was 1/2 at pi over 3, it's negative 1/2 here. That means you end up with a positive 1, and 2 plus 1 is 3. So you go out in that direction and go out 3. Exactly. Here it's negative 1, and so that becomes plus 2, and you get 4. Let me pause right there. And actually, let's connect the dots. And this is cardioid, so it's just going to go like that. We said because it's cosine, you should know it's symmetric about the polar axis. Because that's negative, you should know it's going to go left like we did. And just do symmetric points. It's like this point that was 1 this way goes 1 this way. Point that was 2 that way goes 2 that way. Point that went 3 this along that line goes 3 along this line. And so you don't need to do it anymore on the table, just do symmetric points. And there's your cardioid. So called because it kind of looks like a heart. Correct. They just hit the pole. The limicons will like this point that hits the pole on the cardioid will either be inside or outside on limicon. I'm saying on. I'll go back and compare after we draw some limicons. All right, let's do this one. This one will be a dimpled limicon. And so, yeah, it will not have a loop. Limicon. Let's see, that's not a C, it's a whatever, I don't know what you call it in French. Something like that. But it's pronounced limicon. Oh, come on, just do it right. Not a C. All right, it's a sine graph. Sine is 0, 0. So you get 3. I don't know why I put something other than 3. And you can see, because the sine, which was pi over 6, because that's when sine's a half. So here, what do you get for your radius? 4. That's a half. I mean, that's 1, so 3 plus 1 is 4. So that's a pi over 6, so on that line, 1, 2, 3, 4. There. Well, sine of pi over 2. 1. So you get 3 plus 2. That's your maximum. Due north, you go at 5, you get your maximum point. Now, because it's sine, it's symmetric about the line, that vertical line that equals pi over 2. Let me connect what I have so far. And then these are going to reflect over. So like pi over 6, you don't even need to calculate it again. It's going to be going out 4 just like that one did. And when you're at pi, it's going to go out 3 just like this one did. Because of the symmetry that we have. Now 7 pi over 6, sine is negative now, right? So we're doing 3 plus 2 times negative 1/2. So that means you get 3 minus 1, or 2. So in that line, go out just 2. And then at 3 pi over 2, it's negative 1. So you get 3 minus 2 is 1. And really, that was it. The point that I did put here, that 2 out, goes over here as well because of the symmetry. Now, this is where I was trying to warn you that your table, if you're ever using a table to help you draw a graph, the table only goes so far. Okay, you're supposed to know what the shape looks like. And so what I'm saying is, you come down here, and it connects there. And if you draw a straight line, a horizontal line going across there, you're going to lose points. That's wrong. It has a dimple. It's not straight anyway, ever. So I'm saying it's going to go beyond that and then come back to that point. Okay, it must. It will. Same thing on, obviously it's symmetric. And so it's concave, by the way. We say it's dimpled, but it also means it's concave. And we're done. By the way, one thing I forgot to tell my previous periods, but I mentioned before, here's the pole. How far is the furthest point from the pole on this? It's here, it's 5, right? Which is 3 plus 2, and 3 minus 2 is 1, which is this point. That's the other direction. If I go back to this, 2 plus 2 is 4, that's this point. 2 minus 2 is 0, that's this point. Okay? Alright, now, the next one we're going to change. So, change the 1 into a 2. Okay? Oh, by the way, I forgot to mention, here, you might write this down, on the cardioid A equaled B, the 2's were equal, right? On the dimpled, A was greater than B, but it wasn't too big. That's how you know it's dimpled, by looking at the equation. So if that's 2, if this had been 4 or more, then it'd be the other kind of limit sign without a loop, which is what we're dealing with here. Here, since A is twice B or more, you have a convex limit. And once again, it does not have a loop, but it won't dimple in either. All right, we're going to try to do this one without the table, okay? So, it's sine again, so sine circle has 0, so 2 minus 0 is 2, so we'll plot that point. And mentally, you want to use pi over 6, choose pi over 6 because of sine, so sine is a half, 2 minus a half is 1.5, plot that point. And then at pi over 2, sine is 1, 2 minus 1 is 1, you get that point, okay? At 5 pi over 6, well remember, it's a sine graph, and so it's symmetric. So just come over to this point here, that's 1.5 out, goes over here. This point that was 2 out this way also goes over here. So we just took care of 5 pi over 6 and pi. So we're now down to 7 pi over 6. Sine is negative 1/2, but if you do minus a negative, you get positive. So it's 2.5, which you could also put over here along that line. And then when we haven't done straight down yet, it's negative 1 there, but minus negative 1 is plus 1, so 3. Which, by the way, notice the rule still applies. 2 plus 1 gives you 3 for this farthest distance. 2 minus 1 gives you 1 for that distance. This one, remember, it's another limit, but now it's convex. It's not dimpled. And so it will just go across there and look something like a circle. And that's it. Done. And by the way, it's sine, so it's, like I said, symmetric along the vertical, and negative means it faces down. So, like I said, you can get a lot of this without the table, or without even plotting those points. All right, then there's this one. This would be the limit sign with loop because A is less than B. And like I said, when you're doing the homework, you have your note sheet in front of you, and train yourself to identify it from the equation first. And this one, we're going to go and use the table again. It gets a little bit weird, so the table's going to be helpful. All right. When I plug in 0, cosine is 1, so you get 6, which doesn't quite fit. Just put that first point, like, out here. I mean, it's just off the grid. No, it's doable. And then when cosine's a half, 2.5 plus 1 is 3.5. So that's along this line, go out 1, 2, 3.5. There's that point. Then when cosine is 0, you get this 1, which is here. Now, at 2 pi over 3, cosine's negative, right? So you get negative 1/2 here. That's negative 2.5. Plus 1 is negative 1.5 for our radius. This is where it gets kind of weird. So my angle, I'm at 2 pi over 3, but the radius is negative, so it ends up here. Right? Like my angle's pointing this way, the negative radius goes backwards 1.5. I want to go and connect the dots, what I have so far. So I started here to go through this. Okay, that's just sad. The one thing that's missing, this thing is going to have a loop. And what's going to do is going to hit this point, it's going to go across like this, and it's going to come through the pole. Now, at no point did we get 0, but obviously somewhere in here, R was 0, right? We don't know where, though, because think of this. If I try to solve for when R is 0, I would get negative 1 over 5. This equals 0 when cosine is negative 1/5. I don't know where that is. It will happen, though. You should realize that. It will go through the pole. And so I just don't know what the angle is, where it happens. Now, so look at this. So it goes, it's going to kind of go across there, come and hit this point. Now, we need one more. I didn't do pi. I should have done it first. What do I get there for R? Negative 4. So once again, my angle is facing west, but my negative radius means it's 1, 2, 3, 4 there. And so it's going to go like that. Now let's do the symmetry. Everything else we can just do by reflecting it across. So like this point that's 1.5 this way reflects to here, go 1.5 this way. And it's going to loop back and catch that point. It's going to, in fact, go all the way back to the pole. The point that was 1 above also goes 1 below here. This point that's, what was that, 3.5? So reflected across there. So it comes out there. Not beautiful. But there you go. And then the sun with the loop. So anyway, a lot of times the loop is smaller. That to me seems easier. This one was harder. But there you go. And by the way, the numbers, like, let's go through how to do this. You can get a lot of it without the table. So it's cosine is positive, you know, it goes to the right. 1 plus 5 is 6, so you know that farthest point was 6 away. 5 minus 1 is 4, so you know this point is 4 away from the pole. So like you can get a lot of it just by that analysis. But you do need to get all those points accurate. Okay, good news is roses are easier. Roses are faster. How many petals? 4 petals. Okay. Now it's a cosine graph. Cosine starts out as 1, right? So cosine of 0 is 1, so you start with the endpoint of a petal. How long are the petals? 2. And there's 4 petals. If there's 4 petals, how many degrees between them? 90. 360 divided by 4 is 90. So this one's really, really easy. All you need to have accurately drawn is the endpoints of the petals, and of course the pole, and then you draw your petals, and you're good. No. Listen, those points have to be accurate. Your petals, try not to let them overlap. They don't have to be perfect. The petals themselves don't have to be perfect. Do your best, okay? Well, we're done. How many petals on the next one? Now, sine of 90 is 1. When will 3 theta equal 90? When theta is 30. So our first petal's 4 out. on that line, right? But now, if I do 360 divided by 3 pedals, I get what? So my spacing between the pedals is 120. So from 30, go 120, you're at 150. That's your next pedal. 150 plus another 120, 270, which is due south. There you go. There's your endpoints of your pedals. Now draw your pedals. Technically, a sine graph starts at the pole. Sine of 0, 0. So something like that. Next one is actually very similar. Look, you're still going to start at 30 degrees, right? It's still 3 pedals. But while you start at 30 degrees, the actual endpoint is over here. Right? When you plug in 30, you get sine of 90 is 1, but times -4 is -4. So there's your first pedal. But what angle is that at? 210. And it's still 360 divided by 3 pedals is 120 apiece. So 210 plus 120 is 330. That's this line. So go up 4 on this line for the next pedal. And so I said, that was 330 for the next pedal. If I do 330 plus another 120, I get 450. Where's that? Due north. It's 360 plus 90 is for the terminal of 90. Just for the record, the 210, if I did 210 minus 120, that would have got me to 90 as well. Yeah. Which axis is that symmetric to? Well, I shouldn't say it that way. It's the line theta equals pi over 2. It's not considered an axis in polar, but those both were symmetric like that. All right, decent wind. How many pedals? 8. It's cosine, so cosine starts as 1. So the first pedal, though, will actually technically be over here, right? It's actually very easy, because if you do that, you get 4 pedals. When you split those in half, you get 8 pedals. That's all that's going to happen here. So it's actually, you have to draw a lot of pedals, but figuring it out is very easy. Except for the part, all right, see if I can do this. Every period, I've been having way too many, well, my pedals have overlapped. Let's try it this way. I think that works better. When you try to do them side by side, oh, a little bit of overlap. You tend to get a lot of overlap. This works better. Yeah, thank you. Okay, you get the idea. Then we get to the Lembda skates. You ready? And I want you to write the equation as r equals. And technically it's going to be plus or minus the square root of that. And you can leave like that, although I would recommend and prefer that you go ahead and rewrite it like this. For one thing, that'll remind you that the radius is not 9. The radius is 3, or the pedal length, I should say. And then, look, your first pedal will be at 45 degrees, just like with the rose. So go out 3 in that direction. There's only 2 pedals, though. In this case, there's only 2 pedals. It's not a rose. It doesn't obey the same rules. And so there's only 2 pedals. The other one is 180 degrees away, and that's it. it's technically a little more bulbous on the end than a rose. Maybe not that. But frankly, as long as you have two petals located correctly, you're good. Square root, yeah, it's a little different shape, not exactly the same relationship. That's all I know. And once again, because it's cosine, you just go out horizontally. Cosine starts as 1. So your first petal's at 0. Now, that was the last example. I want to show you a little something. Look at this. Now, I think this is an older calculator, because I think when we did with ours, with these settings, it wasn't that bad, but still, it wasn't good. Watch this. If I change this to the smaller number, I got a better example. Took a little longer. Changed it to a smaller number, it got even better. Still has a little gap there. So I made it even smaller. And then it did really good, but it took a while. Yeah. So I don't expect you to wait 3 minutes. I do expect you to know that that's correct and that's not. Okay? Of course, you're not going to use a calculator on stuff anyway, but if you did the homework to check it and you do something like that, that'd be sad. But it's happened. That's why I'm saying that.